So for our next talk, we have Dr. Erk Subasi. He has a PhD in neuroinformatics, and he's a quant portfolio manager at Limmat Capital Alternative Investments AG. Please welcome Dr. Subasi.
Thank you very much. Welcome everyone. Good afternoon. Thanks for joining me here today. This talk will be about a little fun project actually I did recently. I was mainly motivated by the exciting developments happening in the deep learning field. I had my PhD back in the last decade. That means that time was still sort of in the neural winter times. The machine learning and neural networks were still out of fashion. But you know, being sort of somehow obsessed about tracking the research in the field, I found that for a good cause to investigate what is achievable with the new available techniques. So this is a broad overview of that talk here today. So I said we want to, first I want to somehow motivate you to on the benefits of utilizing these multi-layered abstractions, why it's a good idea actually to utilize such abstractions, also for financial data. So the idea will be, okay, we'll grab some ideas from the deep learning domain and then we will apply them on some financial, one of the most fundamental problems in finance. And by doing so, we will also introduce some TensorFlow, how we can, you know, easily use TensorFlow, how we can apply and embed it into Zipline. Zipline, I guess, as most of you know, is the backtesting algorithm, backtesting library, let's say, which is also powering Quantopian. Before starting, I just want to you know, get a feeling about the audience. How many of you know what an autoencoder is? Okay, not bad. There are a few. How many of, I mean, is there anyone which tried some hands-on experience with TensorFlow so far? Cool. I assume you guys know what, do I have my pointer there? No, okay. I assume, you know what an efficient frontier is. And I know that many of you think that you know who that guy is, but I bet you don't, because he's an imposter. He's actually the dark head of the bad deep learning mafia, which is coming after the presenters who don't use that image in their presentations. Believe me, I've been looking to a lot of deep learning presentations lately, and if you don't have that image in your presentation, so I paid my dues here. I can start my presentation. I mean, one thing is certain, we live in interesting times. What I mean with that is, we witnessed a silent revolution taking place in the last 5 to 10 years. Field after field, we observed deep learning really redefining state of art in various different fields. That was first, what I showed there was from Microsoft research. It was about real-time translation from Chinese to English and vice versa. Last year, again, that's supposed to be again Microsoft, I'm afraid, they managed to go beyond human level on ImageNet classification. This is one of the standard tests, one of the, let's say, relatively challenging tests on the machine learning domain. So now we are computers which see better than, arguably better than humans. Autonomous driving is certainly coming. NVIDIA is working hard, just installing almost a supercomputer on your cars, which will do nothing but deep learning the whole day. They had a very interesting talk, I think 2-3 days ago. I mean, they released new hardware, which looks very interesting. There are very big investments on the healthcare. I'm 100% sure in the very soon future this will have major impacts on our lives. But not only that, I mean, we are already used to being outsmarted by the machine when it comes to sheer computation power, right? But recently, witnessed something else, something a bit more, it feels a bit different. More intrinsic qualities of our human brains, like intuition or creativity, are now being challenged by those machines. So what that means for the financial market setting, what does that mean in the financial market setting? I mean, making an analogy to the AlphaGo case, are we going to see a reinforcement learning, deep learning agent, which is being trained by thousands of years of equal trading experience to a human start dominating our field anytime soon? And I also have a visual for that. This one is also from one of these Google Inception outputs. So is a computer will be the new market overlord? My 2 cents is probably not so fast, but there will be some big shifts in the market. I mean, if you think about the fundamental quant portfolio, quant factors, the bread and butter, momentum, value, growth, whatever. At the heart of all of these factors usually lies a very fundamental human bias. Usually these quantum factors are actually taking advantage of human biases. And that's the reason why they exist still today. But just imagine a market environment where the majority of the players are a lot more rational agents than humans. They don't have this fear, and they are actually trained to take advantage of these biases. And once they start to trading against each other, and they adapt to each other, this will ultimately yield a major shift in the fabric of the markets. So I would say, as a professional, our responsibility is essentially track that change, understand it, and react accordingly. So I'm sort of on that path. I would say this is the purpose of that presentation. But let me just take a step back and give you a sort of a semi-formal introduction. What is deep learning? It's nothing but good old neural networks. I mean, one can even say it's a bit boring. But the only exciting thing about this time is now it works. So the ideas are old. They were there since 50s at least, 60s or so. But a bunch of times we witnessed there's some rising interest in neural networks. People are figuring out some of the problems. They make some progress, and then they face another barrier, which then causes some sort of winter came, and then that suppressed all the research. That was pretty much the case at the beginning of 2000s and end of the 1990s. But lucky for us, in humans in general, I would say, some stubborn researchers kept doing what they're doing. So they insisted, they believed there's some merit in this line of research, and they actually pushed the field further. So what I mean with that is, previously we had suboptimal ways of training our big networks. Therefore, we were typically stuck to the smaller, shallower networks, which were working fine to some extent, but it was not state of art, or they were only at the state of art. It was comparable to other shallow learning algorithms. But what happened was, once we figured out a good way of training these deeper networks, and once we have enough computational power, and once we have enough data, then the whole thing to move to another domain, which brings me why deep learning works in the first place. Well, I mean, probably there are two answers to that. The less interesting one, but more convincing one also, is the top-down approach. You can say the best learning machine in existing that we know is human brains, and these works utilizing some layered network structure. So you get information to your retina that was transformed in an abstracted way to further layers until it goes to your prefrontal cortex or so, that for you to understand and take an action based on that input, it changed so many times shape. But I mean, maybe from a sort of a researcher point of view, why it works in the first place, if you look from the bottom-up view, Natural data oftentimes live in low dimensions, but we don't have access to that low dimensions, which means I mean, you can easily represent that face, different forms of that face, with using only information of 30 to 40 muscle groups in the human face. But the problem is, if you just look at that picture, it's so much richer information there. And there is no straightforward way of going from that information to the level of these low dimensional information. Deep neural nets and in general this multi-layer cascading abstraction concept seems to be doing a very good job actually, just capturing that characteristic, so just capturing these features. So this is the problem I will try to attack in this presentation. I don't think I have to introduce, in a quant conference, the mean variance optimization too much. We are essentially trying to minimize this thing there. The sigma is representing our covariance matrix for some given covariance matrix and some risk appetite and some expected return vector. We are just minimizing this form, and we sort of find the optimal weights, which is again an old idea, which again works nicely, but there are problems again. The problem this time, I mean, as famously put by Michaud, is this: if you just try to run optimization on that problem, it behaves like error maximization approach. So if you have some error in your estimations, in your covariance matrix, or in your return estimates, then just blindly running optimization on that will yield some error maximization. So that means you would actually increase the part of the portfolio which you had highest estimation error. That's not what you want. So in practice, what people do is you somehow try to constrain that matrix. You shrunk that matrix somehow with different methods that can be either bootstrapping or, traditionally, a lot of people use fundamental factors. They use some libraries to do that regularizations. The inspiration I got for that presentation is from this brilliant paper by Lido and Wolf, Honey, I Shrunk the Sample Covariance Matrix. That's a similar approach, actually, that you're just using a statistical measure to constrain your covariance matrix. So now here the question is, okay, now this multi-layered representations seem to be doing a reasonable job. They're actually doing a great job of capturing that low-dimensional information in a rich data. Can we utilize this technique somehow in capturing such essence of a covariance matrix, which cannot be captured by a linear method, and then utilize that structure to shrink your matrix into, and you sort of clean your estimation. Another, maybe just to give you a brief understanding about what I mean with that, a very simple display here. You see some on the top, some data spread in 2 dimensions. We will assume here, so there's data in 2 dimensions. We will assume one data of 1 dimension is enough actually to represent the actual signal, and whatever there is essentially noise. So we can just fit, we can find an axis which would explain the highest variance, and then find an orthogonal axis to that. This is essentially principal component analysis. And then once we drop the second component, we will be essentially just reducing our dimension to 1D, right? Then we will just have a single linear line there, which works nice and fine. It's a very popular thing to do. But the problem is, if your data is, if it lives in such a nonlinear manifold, like in the Swiss roll, then any linear method you would apply to that blindly would result something like in the second picture. So nothing is wrong with the technique, but it cannot really capture the data. On the other hand, This is essentially a very simple problem. The only thing is you should somehow manage to roll it out, that's the roll. Typical way of doing that was, people come up with some kernel method which would map this initial original data to a different domain, to a different space, which is now linearly separable after that kernel transformation, and then you just look some linear separation. But this is, in a sense, expensive and not easy to do in all cases because, as I said, there involves some human intervention. It seems that these multi-layered representations are doing actually a great job in just capturing that. So they really somehow magically training themselves with these layered abstractions to do this mapping efficiently. And this magical little creatures we will use is called autoencoders. Autoencoders is essentially a very simple idea. It's an unsupervised learning procedure. We just want to create our inputs on the output. So that sounds trivial. The catch is we have this intermediate layer. So this is just a simple feed-forward neural network. We have this yellow dots there, which is the input. Then we are forcing our data to go through this intermediate latent code layer, as we often called. And then we actually force the data to be represented efficiently with a small code base, and then we reflect it back, and then we are optimizing this function, this network, such that the difference between the yellow nodes and the blue nodes would be as small as possible. Okay? This is the simple idea about autoencoders. I mean, if you just do that, and if the activation for these nodes on this neural network, if they are linear, then in that intermediate latent code layer, the representation they will capture will be essentially the same with the principal components. So it will be spanning the same vector space, this red layer, with the 3-4 principal components. But if you start utilizing nonlinear activations on these nodes, and if you start stacking multi-nodes one after another, then things start getting interesting. Now you can actually capture, you are doing something similar to principal component analysis, but it's just working on a nonlinear space. As a final additional idea, I mean, this is old school autoencoders. Then the stacked autoencoders appeared. That was like, I think, 2006 or so. That was one of the original ideas, actually, which yielded also a breakthrough. That was one of the papers which was ending the recent neural network winter. And then, in 2 years later, this denoising autoencoders idea emerged, which is we are essentially occluding some part of the data or adding noise, depending on the application. But we still want to reconstruct the input in an uncorrupted way in the output. So that way, we are forcing the network to learn whatever relation exists between the, let's say, not occluded yellow nodes to create the potential information in the occluded nodes. So you're forcing your network to learn the interrelationship across your inputs. And that actually works, that yields to a lot better filters, a lot better feature extractors. This is one example. This is the original picture on the left. You push it through autoencoder with 8 nodes in the intermediate layer, and you almost perfectly reconstruct it. If you try to do that with a simple linear method, if you compress everything to 8 bits of information, then this is what you would get. This is another very interesting demonstration of what autoencoders are capable of. Here, this is about document retrieval We are working with a few 100,000 documents. This is from Reuters business database. The colors are the subjects of these documents. There's some tag on the subject. The proximity and sort of, okay, you have 2,000 word vector, which is like what each of these 2,000 vectors, how probable is that it exists in that document. So you get this 2,000 piece of code. You push it through your principal components, and you just get the first two principal components, and then you map it to that 2D plane, and this is what you get. So here the proximity means things supposed to be also similar subject in for their subject. So as you can see, there are some clusterings for the, let's say the green part is on the corner there. That's nice, but it's still, there's a lot of confusion. If you do the same thing with an autoencoder, this is what you would get. Okay, I hope that motivated you enough on the powers of autoencoders. So we want to implement an autoencoder and actually push our covariances towards that autoencoder and somehow want to denoise our autoencoders by that approach. And to do that, we will use TensorFlow. TensorFlow is that recently open sourced library by Google, which is bringing you a lot of commonly used operations in the deep learning research, and actually it's just a generic tensor operation library. Tensor is nothing but multidimensional array, and most of the machine learning actually can be represented by such a representation. So it's essentially just a very nice tool. It also brings you some auto differentiation capabilities, which are critical for training neural networks. And on top of that, you have the decoupling between the software and the hardware, which means you just define your problem on an abstract level in the software, let's say, level, and you don't really have to think about how your GPUs are going to used in the most efficient way, which is becoming a lot more critical if you're really serious about doing that type of research, because GPUs are a lot more efficient in solving these type of operations. Okay, so how a typical TensorFlow program looks like. It is just a bunch of principles. You lay out a graph. A graph is, you define how separate nodes are related to each other and how the data flows across them. And you define a session which controls that graph, which holds that graph. And throughout that session, you are actually feeding some data to that graph. And the data flows through this thing, and it just spits out whatever you want, whatever you defined. The nice thing is you can define in that graph, you can also define some optimization methods. So you can define a loss function, and you can define, okay, this is how I'm going to train that loss function. And then you just feed the data in, and it finds, you're just using these standard ways of using some standard learning methods. It just optimizes its weights. So how are we going to blend these two worlds? How are we going to use TensorFlow in the Zipline? Zipline is, in the most basic case, it's about two methods. We are first initializing our setup. We are initializing our universe and a context, essentially. And then we have this separate handle data method. It's an event-based library. So every time there's new data arriving, this handle data function is being called, and then you handle that. So how are we going to merge these two things together? We will, in the initialization phase, we will create and define our autoencoder graph. So this TensorFlow graph will be already laid out in the initialization phase. We will define how we're going to optimize that graph. And then we will hold a TensorFlow session, and just embed all this into a context of Zipline. And in the next handle data method, now this is more interesting bit. So Zipline is just pushing us data at every bar, let's say. Once you accumulate enough of these, the red covariance matrices on the left, then you need to feed normalized data to your autoencoder. So we are converting them to a correlation matrix plus some volatility vector. All the information in the correlation matrix is in the upper triangular part. So you are rasterizing that information, adding some normalized form of volatility to that, and you push all these into your autoencoder. Once you do that enough, and once you train your autoencoder, then your autoencoder now actually learns what is important in that universe. Across these instruments, what are the dominating factors? And once it learned that characteristic, what you need to do is just push a new piece of the most recent piece of information, and then it will spit out a shrunk version of the covariance matrix. And then you will just simply use an optimization library to find out your new weights. This is an example of how a regularization, typical regularization look like. You see the sample covariance matrix on the top. It's 7 by 7, and the weights found by some simple optimization method on the right. Below, it's the shrunk version of the same matrix. You probably won't even see much of a difference, but you can tell there is some difference by just looking at the weights. They are slightly different, right? And this is essentially exactly what we want. We don't want, and we don't expect to see completely different matrices unless there's something fundamentally wrong in our sample data. Here, normally, I would actually go to the Linux on my machine and then show you the demo on a Python notebook. Unfortunately, the setup here, we had some problems, so I will only be able to show you a static version of the code.
Can I ask you a question?
Sure.
So in the slide from before with the dogs and with the documents, there was this clear difference between PCA and the deep autoencoder. Here in this matrix, you're saying that it's almost the same.
Here you are converting a 2,000 dimension into 2 dimensions. It's a massive dimensionality reduction. In our covariance matrix that we see, this is, you first do that, you do some form of dimensionality reduction. You sort of find a smaller representation of whatever covariance matrix you have, and then you reconstruct it back. And by that reconstruction, there will be some, so we are not looking here at that intermediate layer, that latent code layer. We are looking at the output. So
that's the dog example, right? The dog example.
Yeah, exactly. Yeah, yeah. I mean, it depends on how noisy your data is. Here, what you see on the up is the original data, and what you see down is the reconstructed data. So it's able to reconstruct that data without a problem. We are not comparing it against a linear method here. So whatever architecture we applied, it was able to capture and reconstruct that covariance matrix afterwards. Let me see. I don't know how easy this will be for you to. So the nice thing is I put the code in GitHub, so you can go there and just grab it and play with it anytime. I will just walk you through the code, so you can, have some idea about how it works, or when I'm already here. So all the, just kitchen sink stuff is another file. For that presentation, I prepared this tiny universe. We have 7 instruments, 5 stocks, 1 gold ETF, 1 bond ETF. The data is almost 10 years old, 10 years long worth of data. This is one of the interesting bits of the code. This is where we lay down the autoencoder architecture in TensorFlow. Probably it doesn't really make too much sense just going through the code here. But essentially, we are defining our architecture in a symmetrical way. So we are just creating this encoder bit, and then we are creating the decoder encoder bits, and then we are attaching a loss function and a training method there.
Is there a specific architecture you tend to use all the time, or is that?
It will change from I think the universe to universe. Also, it is obviously a function of your universe size.
Right, but is there any sort of rules of thumb?
Well, I just played with some things, maybe with 10 or so different architectures. They oftentimes yield to similar results. If you have too big of a network, then you learn everything. Then you don't really get much out of that. If your network is too constrained, then probably you are just not learning enough. So it's a bit of trial and error, and there's
typical overfitting problem.
Exactly, and there's now the joke about deep learning in general. Previously, people were spending a lot of time on feature engineering, but this time now we're really playing by triggering our networks structures. That's part of the problem, I would say. But one thing, I will come to that. For such a small universe with 7 instruments and with daily data, that type of approach doesn't really, it won't really bring that much on top of a linear method. That's not really the point here. The point is just laying down the architecture, and once you want to get serious about that, you need to apply a lot higher frequency data.
Usually on the PCA side, people always did sort of 10-to-1 ratio reduction in terms of number of dimensionalities. I was just curious to see if you had any sort of basic rules of thumb.
So the way I typically did it, so the input layer it has some certain number. Then I go slightly higher and sort of over-representation of that input, because I'm using denoising autoencoders. So there will be some sparse encoding in that layer. And then I start going down another 2-3 layers with, let's say, halving, or maybe going another factor down. And then that's pretty much it. So typically I tested in total 6 to 8 levels of that, not crazy. That's.
Okay, thank you.
So in that Deep-Shrunk comat part, there's 2 regimes of operation. The first one is if you provide a TensorFlow context. So this is essentially the dictionary which holds your graph and all the TensorFlow sessions. Then, so if you don't provide that, then it assumes, okay, I will create this for you. So it just goes and creates that graph. Creates the autoencoder, creates a TensorFlow graph, and then feeds the data. If it finds a TensorFlow context, then it assumes that, okay, someone previously created that context for me, and I will just apply newly received data on top of that. So that was actually a handy way of utilizing it in the Zipline setting. That way you would be able to, you just start with some small number of observations, and you gradually train your network with new incoming data. I was going to show you some covariance matrices, how it develops in time. Unfortunately, it won't be possible today. This covariance data set is doing some boring parsing work for you. Okay, this is, for example, one example here. We grab 700 days of data. Our co-lengths, our covariance lengths are 250. So we are estimating, given the last year's data, our covariance matrix. And then we use this 450 covariance matrices to train our autoencoder. So we just smash everything here. And then this is, for example, the architecture I chose for that one. It's, let's say, 7 by 7. That means 42, 21, 28 data points. So this is upper triangular elements of the correlation matrix plus the volatility diagonal elements. So 28 points to input. So from 28, I'm first going to 64, which is actually quite a lot. But I'm also heavily denoising it. So it's for every node, there is a 50% probability that it will be dropped. And in the next layer, I will go to 32 bits and then 4 bits, and then just construct everything back.
So I have a question. I think I missed it, but what are the examples? They're daily? Or they're
Yeah, they are daily. This is daily data.
So the daily...
Covariance matrices, rolling window of covariance
So
matrices.
there's substantial overlap.
Yeah, exactly. Yeah. This also actually helps if you have so much noise. That type of just sort of showing similar things over and over helps actually. But this is also the typical setting in that domain. If you're working in daily data, you don't really have a way around that. You won't see massively different covariance matrices from one day to another.
Some people like bootstrap resale,
Mm-hmm.
things like that. Should you try it?
Yeah, that's a good point. I did think about it. It's not here, but I think it's a brilliant idea. In general, what you can do, for example, is you really just perturb your data a bit and create a lot of additional covariance matrices and feed all of those. You can even use, I think, highs and lows of the day, and then just looking at these range, you can just try to come up with alternative ways of covariance, some more creative ways of bootstrapping. With Wolf, Wolf has a problem if you are not working on solely on stock universe, because they're just they're a bit more too aggressive to shrink everything to an identity matrix, right? So in that sense, if you have a universe where a lot of, let's say, a multi-asset class universe, actually that was one of the first things which motivated me to think about these things, because I was looking to shrink a multi-asset class universe covariance to something reasonable, and Wolf approach doesn't help. Here, it yields better results than Wolf. I haven't compared to principal component analysis. For that size, I don't expect, actually. I don't think it will yield anything. And again, this is really not I'm selling here. The main purpose is just to lay down the architecture, and if you want to really get the real benefit out of that, you need to really go to bigger universes and also to higher frequencies. But I don't see a reason, well, of course, but I think there's a good case for such a nonlinear approach to capture better characteristics. Okay, here, this is the original sample covariance estimation, and this is the autoencoder corrected one. I don't know if you see any difference here or if this excites you too much. Let's go to the backtest. Here I basically embedded these two methods from Zipline into a single method, and just for the, it's easier to run. And that guy, you can say, if you want to use the original sample covariance estimates or the autoencoder shrunk version of that. Here we will run this network, similar one, for 10 years. And this is essentially what you get if you use your sample covariance estimates. You got the blue line using the autoencoder, you got the green line. Again, that doesn't mean anything. I mean, it can be just random as well. And I obviously run a bunch of things. Majority of them looks better, but there are still the worst ones as well. But for such a size, I would say it's a bit arbitrary. But what, I mean, the point here is it's behaving the way I expect it to behave. It's doing something reasonable. Yes?
What's the reason they're running it on very small universes in terms of shrinking correct from that matrix? The benefit really comes from a large portfolio. Have you tried something like SP100?
The biggest, I mean, this is sort of, that was really my side project. It's not really something I'm doing the full time. So it was sort of a nighttime project. In that regard, I was limited by the resources in terms of time I can spend on that. I mean, the biggest universe I ran, it was a FTSE 100. It worked there without any issue. But I think the bigger issues come with training size. So I think on the daily data, with the covariance differences you will observe from one day to another, probably at a universe of 100, there might be some benefits. What I observed there was for FTSE 100, it was slightly better than that, but it was not massively better. But again, this is, I wasn't trying to really come up with the best network structure which will yield to the best backtesting results. That's not really the point. I was just building my case for the next slide. But yeah, the biggest network I trained, it was 100. I think it should be without any issue possible to use for bigger networks as well. So, but let me go quickly through to the next idea, this anomaly detection. I think this is a lot more interesting. Just assume that you're estimating your covariance metrics in a real-time fashion. You're just getting some real-time data and making estimations, spitting out some estimations. And at one point, there is some bad piece of data, and your covariance matrix is massively corrupted. For those scenarios, such regularizers are extremely useful. So you feed this corrupted observation, and this is what you would get from your autoencoder. So it essentially just flawlessly just cleans your observation. I was also going to show you how that can be tracked in a sort of a real-time session in the TensorBoard. TensorBoard is a visualization tool from TensorFlow. There you can log your loss for that. And loss is essentially the difference between your input and output in that setting. Since it's defined so nicely, you can just log this thing and you can just track. So in normal times, let's say you're just getting data, running it through your encoder, you just have something very stable, and there's a broken piece of data, and then immediately that loss function will jump, and you will still get the corrected version of that covariance matrix. So you're sort of in a less risky environment in terms of trading, but there might be two reasons for that jump. Obviously, one of them, maybe the data is broken, or maybe there's some fundamental change in the market. So if that happens, you will get an alert, and you will actually just go there and look, okay, what's going on? Why my covariance matrix just changed so much drastically? And this is a very natural way of capturing that. Of course, you can have some other ways of doing that, but that just captures that difference in a very natural way. So that's, I would say, pretty much it on the okay, I have some slide here about that. So the one on the left, the upper one is the 7 instruments case. You see below a bunch of different other neural network architectures which are trying to learn the same data. And what is important there is at the very bottom is your sample covariance. So whatever you try, it essentially yielded a bit better results. It's not massive, but it's just something. And the same thing for, I also ran for Dow Jones. For 30 names, you will also get a similar picture. I started that talk by saying we live in interesting times, and by preparing that presentation, that just remembered me this ancient Chinese saying, "May you live in interesting times," which is supposed to be actually a curse. So my feeling right now is we are really in an interesting time. There is so much power out there. Just TensorFlow is such a brilliant library. You will have access to that so easily. You can run this on Google Cloud. They have recently made it available to run their notebook, IPython notebook-like things running on their servers. So you will have all that power is on the tips of your power, and there is very good reasons to believe that this multi-layered representations, the whatever which seems to be contributing to deep learning work, it will have an impact also in the financial market. But we just need to find the right balance between the two. So we don't want to overfit our data, and having such powerful libraries, it makes it so easy. So we need to know what we are doing, but we cannot also tolerate not just closing our eyes on the developments and saying, okay, I will just run my old quant models all the time and that's it. So I think it's up to us to say if it's really an interesting time, or in the Western setting or in a Chinese setting. Yeah, thank you very much. Thanks for the attention.